We were looking at a paper today that completely challenges one of the most fundamental assumptions in generative AI, the idea that a diffusion model actually needs to know what time it is. The paper is called The Geometry of Noise: Why Diffusion Models Don't Need Noise Conditioning. It's coming out of Google research by Mugtabas Array Artikan, Mauricio Del Brasio, and Payman Malanfar.
And the core question they're answering here is pretty fascinating. Can generative models work without explicitly knowing the noise level, that time variable t?
Right, and the key insight they bring to the table is that yes, they absolutely can. These autonomous or blind models aren't just taking random guesses. They are mathematically proven to be performing a very specific form of Riemannian gradient flow on a marginal energy landscape.
Exactly. And the solution to the whole paradox of how a blind model does this is brilliant. The raw energy landscape actually has a geometric singularity, an infinitely deep potential, well, right near the clean data manifold.
But the learn vector field implicitly learns a local conformal metric, basically a gain control that perfectly counteracts that singularity.
Right. But the practical takeaway, and this is crucial for the high density summary here, is that this only works if you use the right parameterization.
Yeah, you have to use velocity-based parameterizations like flow matching. The authors mathematically prove that if you use standard noise prediction, like an epsilon DDPM setup, it is structurally unstable in the blind setting.
It completely fails due to a Jensen gap that acts as a high gain amplifier for errors.
Okay, so that is the ultra-dense summary of what we're covering. This is AI Paper Podcasts, and we are going to really get into the weeds of this geometry today. So, to set the stage for you, let's talk about standard diffusion. Stable diffusion, DALI, all the big ones you interact with, they all take an input image that's noisy and a time step.
Yeah, always. That time step 2 is the coordinate. It tells the network, hey, this image is 90% noise, or this image is only 10% noise.
And that's incredibly crucial because the direction you need to move the pixels to clean them up is completely different depending on how much noise is currently there.
Exactly. I mean, if you're at high noise, you need to make massive structural changes to the image. If you're a low noise, you're just refining tiny details. The standard assumption has always been, if you don't give the model that time step, it just won't know which tool to use.
It's a difference between needing a sledgehammer and a scalpel.
That's a great way to put it. Without twin, it'll be lost.
But this paper is focused entirely on autonomous models, which implies they are operating completely without that map.
Right. There's been this disruption in the field lately with things like equilibrium matching and blind diffusion. The core idea is to learn a single vector field, let's just call it F the theta of u, that takes a noisy point and outputs a direction without ever being told what it is.
Which sounds great in theory, right? You get a simpler architecture, no scheduling headaches during inference, but it creates this massive puzzle. If I show the model a pixel value, how does it know if that's a signal pixel or a noise pixel if I don't tell it the context?
And that is exactly the paradox the authors start with. They ask, what is the underlying landscape being optimized here? If the noise level is treated as a random variable, meaning the model doesn't know it, what geometry are we actually traversing to generate an image?
And this is where things get mathematically pretty scary. They start talking about the marginal energy.
Yes. So imagine an energy landscape. In physics or ML, we usually want to roll a ball downhill to the lowest energy state. Here, the lowest energy is the clean data. They define this marginal energy as the negative log likelihood of the marginal data distribution.
Okay, stick with me here. So the clean data is sitting at the bottom of a valley.
A very specific kind of valley. The authors actually derive the gradient of this energy and prove that as you approach the clean data, the bottom of the valley, the gradient explodes to infinity.
Wait, infinity?
Theoretically, yes. It forms an infinitely deep potential well. It's a true mathematical singularity.
So if I'm a blind model and I'm trying to descend this landscape to generate an image, and I get close to a real cat or dog, the slope just becomes a vertical cliff.
Precisely. And if you think about standard gradient descent, if the gradient goes to infinity, your step size effectively becomes massive. You'd overshoot the target entirely, bounce out, or just diverge completely. The model really should crash.
But clearly it doesn't because we have empirical results showing these blind models actually working. So how does the model survive the cliff?
This is the real aha moment of the paper. They prove that the autonomous model isn't performing standard gradient descent at all. It's actually performing Riemannian gradient flow.
I feel like we need to define that for the non-mathematicians in the back. What makes it Riemannian?
So in standard geometry, Euclidean geometry, distance is fixed. A step of size 1 is always size 1. But in Riemannian geometry, the space itself could be curved or warped. You have a metric tensor that defines how distances work locally.
It's almost like having a ruler that shrinks or expands depending on where you are standing on the map.
That is a perfect analogy. The authors decompose the vector field, learned by the model, into three distinct components. There's a natural gradient that pulls you toward high density, a linear drift, and a transport correction. But the magic component is what they call the preconditioner, or the effective gain.
The gain.
Yes. Think of it as an automatic braking system. They mathematically show that the model implicitly learns a gain term derived from the posterior noise variance. As the trajectory approaches that infinite well of the data manifold we just talked about, this gain term shrinks towards zero.
So the slope is going to infinity?
But the ruler, the step size the model actually allows itself to take, is shrinking to zero at the exact same rate.
They just cancel each other out.
Exactly. It converts an infinitely deep potential well into a highly stable attractor. The model essentially learns to brake automatically as it lands on the data. It turns what should be a crash into a perfectly smooth landing.
That is incredibly cool. It's like the model is deriving its own safety mechanism directly from the geometry of the data itself.
It is. And this decomposition totally explains why blind models work in theory. But, and this is the part that I think is most relevant for anyone actually building these architectures, the theory only holds if your architecture allows that cancellation to happen.
Which brings us to the stability analysis section of the paper, because they compare two very different ways of parameterizing these models, noise prediction versus velocity prediction.
Right. And if you've worked with stable diffusion, or DDPMs, you're highly likely using noise prediction. The network tries to predict the added noise, epsilon.
And the paper literally says, do not do this if you are going blind.
Do not do this. They identify a massive structural instability. In the autonomous setting, if you use noise prediction, the effective gain we just talked about, that braking system, it scales as 1 over the noise standard deviation, 1 over b of t.
Okay, let's trace that math for the listener. As the image gets cleaner, the noise level, b of t, goes to 0.
Which means 1 over b of t goes to infinity.
So your gain is just exploding.
Correct. You have an exploding gain multiplier acting directly on your prediction errors. They formally call this the Jensen gap. Because the model doesn't know the exact time, it has to essentially average over the possible times it could be at.
Right.
But because the function is nonlinear, it's convex, the average of the function is not the function of the average. That gap, that tiny mathematical error, gets fed straight into a high-gain amplifier.
So tiny little estimation errors in the network get blown up into massive artifacts in the final output image.
Exactly. And they show this empirically, which we'll get to. If you train a blind DDPM, the results are just terrible. High-frequency noise, really messy textures. It just can't settle down because the gain is screaming at it to make huge changes.
Contrast that with velocity prediction or flow matching.
Velocity prediction targets the velocity field directly, usually something like v equals u dot. The authors prove that this parameterization satisfies what they call a bounded gain condition.
Meaning the gain doesn't run off to infinity.
Right, it stays completely finite, effectively right around 1. So instead of amplifying the uncertainty about what time it is, the velocity model absorbs that uncertainty into a smooth, stable drift. It averages the vector field in a way that respects the geometry.
So if I'm an engineer and I want to build a model that doesn't need a time input, maybe just to simplify my serving stack or cut down on scheduling logic, I must use flow matching or velocity prediction. Noise prediction is entirely off the table.
Mathematically, yes. Noise prediction is structurally unstable in the blind setting. Velocity prediction is inherently stable. It's not a tuning issue. It's a hard constraint derived from the geometry itself.
I want to pivot to something else they mentioned in the paper, which is this idea of dimensionality, because there's a deeper philosophical question here for you as a listener. How can the model possibly know what to do if it doesn't know the time? How does it know if a fuzzy blob is inherently a fuzzy blob or a sharp object covered in noise?
This is where the paper draws a really important line between two regimes: local proximity and high-dimensional concentration. We just talked about local proximity. That's the braking mechanism near the data manifold. But the high-dimensional part is truly mind-bending.
This is the whole curse of dimensionality actually becoming a blessing, right?
The blessing of dimensionality, yes, in high dimensions. And remember, images are extremely high-dimensional spaces, thousands or millions of pixels. Random vectors behave very predictably.
Give us the visual for that.
Imagine a high-dimensional sphere. The noise creates a kind of shell around the data. In high dimensions, the probability mass of the noise doesn't just spread out evenly like it does in 3D. It concentrates into a very thin, dense shell at a highly specific radius.
So simply by looking at the norm or the magnitude of the noisy image, the model can instantly calculate that radius.
Effectively, yes. The paper argues that in high dimensions, the geometry of the noisy observation physically reveals the noise level. The model doesn't need you to explicitly tell it T because it can dynamically measure the noise radius from the observation alone.
They actually ran a toy experiment on this with concentric circles to prove it, didn't they?
They did, and it's a great demonstration. They took a simple 2D data set of concentric circles and projected it into high-dimensional space. In 2D, the blind model completely failed. It got confused between the inner and outer rings.
Because in 2D, a point sitting right in the middle could be a noisy version of the inner ring or a really noisy version of the outer ring. The ambiguity is impossible to resolve.
Exactly. But as they increased the embedding dimension for the exact same data set to 8, then 32, then 128 dimensions, the blind model's performance seamlessly converged to the oracle model, the one that actually knew the time step.
That is wild. So the ambiguity literally vanishes just because you gave the noise more dimensions to spread into.
The posterior distribution of the noise level collapses into a sharp spike. The model looks at the data point and says, oh, based on this high-dimensional geometry, I am definitely at time step 0.7. It infers the time completely implicitly.
So blind models aren't really blind at all. They're just reading the braille of the high-dimensional geometry.
That's a somewhat poetic way to put it, but yes, they are inferring the temporal state directly from the spatial state.
Let's talk about the real-world results, because the toy models are great, but we want to know if it generates good images. They tested this on SAFAR 10, SVHN, Fashion MNIST. We touched on it briefly in the intro, but how stark was the actual difference?
It's completely night and day. On SAFAR 10, they looked at the FID score, the Frege inception distance where lower is better. The blind DDPM model, the unstable noise prediction one, got a score of around 40.9.
Which is not exactly state-of-the-art.
It's bad. The images look staticky, broken, the colors bleed. It's a failed model. But the flow-matching blind model, the one using velocity, it got an FID of 2.61.
And 2.61 is basically right at the top tier.
It's perfectly on par with the conditional baseline. It implies that removing the time variable didn't hurt the performance even a fraction of a percent, provided you use the correct velocity parameterization.
This feels like it unifies a lot of disparate concepts in the field right now. We have optimal transport over here, we have standard diffusion over there, we have this new equilibrium matching stuff popping up.
It really does feel unifying. The paper explicitly positions this autonomous framework as the bridge. It connects transport, which is moving mass from plane A to point B, with restoration, which is cleaning up noise. It shows they are literally just different views of the exact same Riemannian flow on this marginal energy landscape.
And it really challenges the dogma that we need to micromanage these architectures with intricate schedules. We spend so much engineering time tuning noise schedules, linear, cosine, sigmoid.
And this mathematical proof suggests that if the geometry is set up right, the model can easily find its own schedule. The concept of time is already inherent in the energy landscape.
So, projecting forward, what does this actually mean for the future of generative models? Are we just going to stop seeing time embeddings in units entirely?
I genuinely think we might. If velocity-based models are inherently stable and can infer the time step purely from high-dimensional statistics, explicit time conditioning just becomes totally redundant. It's an extra parameter matrix we just don't need. It simplifies the architecture significantly.
And potentially the inference serving too.
Potentially, yeah. It definitely simplifies the training objective. You're just learning a single static vector field. You don't need to worry about balancing the loss weights across 1,000 different time steps nearly as much, because the Riemannian geometry handles the natural weighting for you.
I love that. It's like we've been using training wheels on these models for years, and this paper just proves that the bike stays up completely by itself just because of the physics.
Exactly. The physics of high-dimensional probability.
Before we wrap up the main breakdown, I want to go back to that infinite well image. I think that's the visual that really sticks with me from this deep dive. The idea that our data sits at the bottom of a gravity well so deep it technically breaks the math, but the neural network somehow builds a parachute on the fly.
It is a beautiful way to visualize it. And it really highlights why machine learning is fundamentally different from just pure optimization. If you just naively optimize the raw energy landscape, you'd fail instantly. But by learning the vector field instead, the network learns the preconditioner. It learns how to approach the singularity without dying. It's almost like meta-optimization.
So to comprehensively recap for everyone listening today, the paper is The Geometry of Noise.
Right. And your key takeaways are, number one, you do not need explicit time conditioning in your models. Number two, autonomous models perform a Riemannian gradient flow on a marginal energy landscape. Number three, to actually make it work in practice, you absolutely must use velocity parameterization, like flow matching, to avoid the gain singularity. Number four, standard noise prediction is structurally unstable in this setting.
And number 5, high dimensions are always your friend.
Always. The blessing of dimensionality.
So here is a final thought to leave you with as we sign off. We've firmly established today that these models can infer time, which is really just the noise level, purely from the geometry of the data itself because of that high dimensionality.
Right.
It makes you wonder, what else are we explicitly feeding these models that they could actually figure out entirely for themselves? We feed them class labels, complex text embeddings, explicit style tokens. If the geometry of the raw data is rich enough,
Is there a world where we stop conditioning models altogether?
exactly. Do we just let them navigate the manifold on their own? Are we fundamentally over-conditioning our AI and holding it back?
That is the ultimate question moving forward. If the data really contains everything within its geometry, maybe we just need to build the right vector field, get out of the way, and let the flow happen naturally.
Definitely something to mull over as you look at your own architectures. Thanks for listening to this deep dive on AI paper podcasts. We will catch you in the next one.